And thank you for the introduction, Marcelo. So I'm going to continue the discussion about the INRF model that Marcelo had. And I'm going to talk about modeling simple and complex cell activity and how we can model it with the INRF paradigm, with a variation of it. So this is a figure from one of our presenters that shows the response properties of simple cells in V1 and complex cells in V1. So in the first row, we see simple cell response. And if you look at the third column, you see the response of a neuron. It's a computational model, but this is similar to how a neuron would respond to a stimulus, to a sinusoidal stimulus with different orientations. So it has selectivity for a particular orientation, and as you shift the orientation, the response of the neuron diminishes. So the difference between the simple and complex cell is seen in the first column. So for the simple cell, if you shift the phase of the stimulus, then the response of the neuron degrades. However, for the complex cell, it's shift invariant, meaning that it doesn't matter if you shift the phase of the stimulus, the neuron will respond the same. So Hubel and Wiesel, based on the response properties, they thought that the simple and the complex cell, they follow a hierarchical model. So you see on the left that LGN neurons are with specific, that are oriented, aligned in a specific orientation, are connected to a neuron in V1. And and that gives the response properties of the simple neurons. And for a complex neuron, we see different simple neurons that have selectivity for the same orientation, but different phases. They're connected to a neuron in V1, so that gives them the phase invariance. However, there have been evidence challenging the exclusivity of the hierarchical model. Few of them are that there is direct LGN input to complex cells. There are visual stimuli that drive complex cells, but not simple ones. And there is persistence of complex cells responses when simple cells are inactivated. And there is this opinion that there is a continuum and not a direct dichotomy from simple cells to complex cells. So, okay, so this is the INRF model. I'm not going to go through it again. It has the linear part and the nonlinear part that Marcelo discussed about. And it's one shot. So the variation that I'm showing here, it's that we have an iterative model. So this iterative model is based on the Wilson-Cohen, and basically Hx is the external input, alpha is the activity, and the integral here shows the interaction between different units. Initially, the Wilson-Cohen model was a neural mass model, so it was modeling neural populations. But later, it was used also for neural units. And this is a variation by Marcelo that if you see in the nonlinearity in the integral, there is this other term that indicates the backpropagation. We could indicate the backpropagation from the soma back to the dendrites. So this is an iterative model for the parallel model, meaning that there is a direct input from LGN cells to cells in V1, and those cells in V1, they can produce, we claim, complex behavior. So here, the second term. The J is the activity of the unit of the neuron. The second term is the linear part. Phi K is the linear, we can call the linear receptive field, which is a Gabor. W, the third term is the nonlinear part, where W is the shifted, is the weighting of the nonlinear contribution, and it's a shifted Gabor of the same orientation as phi K in that particular case. And I0 is the image, it's either the raw image or the image convolved with the difference of Gaussian, indicating that the input passed through LGN. And alpha is a factor of the backpropagation. So, and we iterate this model until the J converges to a value. So, okay. So lambda is the contribution here for the nonlinearity. So here, what we'll do is we will change lambda and we see the behavior of the model. So for lambda small, we see that the neuron or the unit has a simple cell behavior. So we see the orientation tuning curve on top. Below, we see the phase response, and we see that the phase diminishes if we shift the stimulus from its preferred phase. But as we increase lambda, we again see the same or similar orientation tuning curve, but we see that the unit becomes more invariant to phase changes of the stimulus. And so, and as we increase further the lambda, we see that it's the unit becomes completely phase invariant. So maybe those numbers were not good to show that there is a continuation from simple cell to complex cell behavior, but there is a gradual change from, like if you see the green, from this phase selective to phase invariance. So we saw that this iterative model works, and with a nonlinear neuron as we have it, you can have a complex response if LGN input is directly projecting to a V1 neuron. So this is the hierarchical model, similar to the one proposed by Hubel and Wiesel. And the only difference with the previous model is inside the nonlinearity, sigma 2 is this convolution of the linear filter with the image. And actually, I should also say that the nonlinearity in this case and in the previous case is an even function, is like an absolute value raised to the power. And yeah, so again, we iterate until the J, the activity, converges. So here, this is kind of a preliminary work. So I got, as I increased lambda, I got phase invariance, but my orientation tuning curves were not so good, so I was a bit timid to show them. So, so Marcelo was kind enough to give me his results from the one-shot model, which models hierarchical connectivity pattern. So yeah, this is for lambda equals 0. We see that it's phase selective and the orientation tuning curve. And as we increase lambda, we see that the phase the selectivity to phase, there is less selectivity to phase. And yeah, this for lambda equals 5. So it has the behavior of a complex cell. So the iterative should work. It's just that I didn't have time. I apologize for that. Sorry, Marcelo. So my timidness in showing my results goes well with like one of the chapters from these books. It's called 23 Problems in Neuroscience. And I guess it follows the same, it's like a mathematician, Hilbert, I think in the beginning of the 20th century had like proposed 23 problems in mathematics, or that needed to be solved. So this goes in the same vein. And again, Olshausen, sorry, but it's very good. So I'm gonna talk about this chapter, and Olshausen and Field, they claim that we just know 15% of what V1 does, and the other 85% we're kind of like unaware. So basically, they say that we're doing the neurophysiologist that goes into looking for neurons, does some kind of bias sampling. So they look like for big soma, they look for neurons that fire more rigorously than usual. And they claim if they find a neuron that fires, but doesn't fit kind of like the model that we expect, like with a nice orientation tuning curves and phase invariance and all that, they kind of like say that it's visual and responsive. So they kind of like put it under the rug. And this kind of reminds me kind of like how societies and governments kind of like, they saw the good neurons, like, you know, how society is. We put them in the stump, and then they hide the other stuff, the other people. So this is the non-visually responsive neurons. So yeah, this is how they claim it's 15% that we know. So let's say they select the neurophysiologists select 40% of the neurons that they look for, and then from those 40, even those 40% or 30% that they select, they have very bad predictive power. So when they go into real data, the variance they can explain is around 30 to 40%. So the known is this small white table, the unknown is like this deep blue ocean. So, okay. So I just picked some other parameters. For example, the INRF model, and for example, in this particular case, the backpropagation factor is 1, so there is bigger backpropagation, and I get something like that. So if like the neurophysiologist was getting something like that, they would just discard it. So, okay, so another thing that we know in V1 is that there is a dimensionality expansion from LGN. So for example, for its input, so there is 100 times more inputs in V1 compared to LGN. And most of the neurons in V1, they are silent. So there has to be something going on. So one proposal is that the neurons in V1 are mostly silent, possibly because of recurrent inhibition. So this is kind of like an architectural design. It's not real neurons. They took it from Ramon y Cajal and put it together. So you can look at it different ways. I look recurrent connections. So, and this is the Rosal model of inhibitory recurrent connectivity, which is similar to Wilson-Cohen. So basically here, we will have a set of neurons or units, and the last term on the right is the interaction between the different units. So this GMN is a weight that depends on the selectivity of different neurons. So if two neurons have very similar selectivity, this weighting will be high. So if one of the two neurons become active, which is indicated by alpha, it will inhibit the other neuron. So it's kind of like a very competitive environment for the neurons, and whoever is activated first suppresses the other that have similar selectivity. So I'm gonna show you even more preliminary results that I need to work on. Not yet. So
there are some questions.
There is question.
Well, I'd like it to be so.
Yeah.
3 more minutes.
Okay, yeah, I'm done, almost done. So this is the recurrent model, which tries to be similar in some way to Rosell model, but we have again the nonlinearity and the backpropagation, and we get also the feed-forward input from either the parallel or the hierarchical model. So typically this is how it's done. You'll get a feed-forward activation, and then there is this competition between the neurons. And yeah, what we get is I get no winners, but yeah, I need to work a bit more on the coding and the model. So we expect that so this is the activity as a function of iteration for different units. So we would expect eventually, as we work on the model, that one of the activities will stay stable and it will diminish the other activations. So I'm almost done. Okay, conclusion. Yes. So, okay, so the INRF iterative model can replicate a continuum of responses from simple to complex like for parallel connectivity patterns. The hierarchical model shows phase invariance as we increase lambda, and gracefully, Marcelo gave me his results. It also shows this continuum from simple to complex like behavior. And for most parameter values, though, the model shows different response patterns that could be classified outside of the 15% one. So maybe, yeah, so recurrent inhibition could be a key to that because it pushes units to silence and it's in accord with like sparse coding. And we hypothesize, we still don't have results, that the neurons that dominate in this competitive interaction would show simple complex responses consistently. And maybe these are the ones that are picked by the neurophysiologists. Yeah, more tests to be done for that. So thank you.